do that. Yeah, I got to fix this. Motion in a vertical circle. Okay, so today we're going to talk about vertical circles. We left it on Friday, Sean, because I wanted to go through this with everyone here. I think I have to. I heard Alex say when we were talking about this before, heard him talk a little bit about it, but so let's just sort of review that. If I swing the rubber stopper on the string in a vertical circle, what now becomes sort of in play? Gravity. Exactly. So as the rubber stopper is going up, slowing down, the force what? Decreases. And as it's going down, the speed should increase, which is going to actually more tension on the string, right? When is there the least amount of tension in the string? Right at the top. And if I could show that if I go slow enough, at some point, right there, right? The string actually has zero tension in it, and it actually falls right off. Kind of thing, right? Just like when I showed you guys that video, didn't I? Where the guy's driving the car in the loop, right? So they have to go fast enough that they don't fall off. But the problem with going too fast in that instance was what? Too much G-force. Yeah, knock them out, right? Okay. So the math here is kind of the concepts is pretty easy. The math, sort of the subscripts, the sign starts to sort of get complicated here.
Subscripts again?
Yeah, subscripts.
Or subscripts?
Consider a ball moving in a circular path as shown. Okay, we've seen that. We've talked about it. Blah. Oh.
Whoa.
We talked about what happens to the speed of the ball. We know that what? Increase. When is it traveling its fastest?
Go down. At the bottom.
At the bottom. It's traveling its fastest right at the bottom. What happens to the tension of the string? Increases at the bottom, decreases on the way up, right? Should I jot that in here? Speeds up on the way down, and lessens on the way up. Oh man, these are old. I got to change these slides. Okay, you probably want to draw this picture. I'll give you a couple minutes while I do my attendance. Draw this picture, and then we're going to talk about the various formulas that come out of this here. You guys get the picture drawn? So what do you think all these various subscripts and markings mean? Vmin, obviously, I think means minimum velocity. Vmax is the maximum velocity. What do you think well, we know what FW means, right? Weight force. So we're talking about gravity there. FS1. It's a force. S stands for, I just said string force. That's all it is. Okay? So string force 1, string force 2. Is string force 1 and string force 2, are they equal to each other? No, because we know that the tension in the string is going to change, right? Okay, so because of gravity, the speed of the ball is not uniform. If the question says that it's a vertical circle, but it says UCM, it just means that it's average uniform circular motion. Okay, don't get all freaked out and worry about that kind of stuff. Okay, the ball accelerates on the downward path and decelerates on the upward path, right? So we are accelerating here and decelerating there, right? Because of gravity. Speed is a minimum at the top and a maximum at the bottom. And I think really for the most part, that's pretty much common sense. It's the math here that sort of is the problem, right? The concepts are pretty straightforward. Everyone's taken a rubber stopper and whirled it around vertical circuit. Maybe not a rubber stopper. Okay, so at the top,
Oh my God.
I'll let you copy that and then we'll explain. I'm going to say FC1 centripetal force 1. The total centripetal force is a combination of string force 1 plus FW. And they are both in the same direction here, right? This is FS1 and this is FW. I've indicated them as equal, but that may or may not be the case, right? I just drew arrows, that's all. Don't think of them as being to scale. The string force, the centripetal force is a total of mv squared over r. We learned that the other day. And that v is the minimum. So I put down mv min squared divided by r. And that's equal to string force 1 plus Fw. At the bottom, we've got the opposite. Right? Centripetal force 2 is equal to the string force minus the weight force. This one is the string force. This one is the weight force. Okay. Now, would you agree that Vmax is greater than Vmin? Of course, by definition. Would you agree then that the string force 2 at the bottom is greater than it is at the top? Yes, because the mass is going to remain the same, the radius is going to remain the same. Vmax squared is going to be greater than Vmin squared, so Fs2 must be greater than Fs1. So the string tension is greater at the bottom.
Yeah, we already discussed that.
Yeah, we already discussed it. Okay. This implies then that there's some velocity below which the ball will not move in a circular path, right? There's some speed that, what happens? It just falls apart, right? Like I showed you before, right? What if there's no string? Will that be the same thing? This guy isn't going to play, is it? Okay. The car does not have enough speed to make the loop-to-loop, same as the video I showed you before. It's not going to play, is it? No, it's going to just hang up. It's too bad because it's cool because it goes like this and then it falls off. Oh. Yes, it crashes and burns. It's awesome. Okay, I'm just going to do this. I know it looks stupid, but I'm going to do it this way. That way I can control a little bit more.
Yep. Control there.
Go to the next page. The minimum value is when the string force is equal to 0. Would you agree with that? When there's no force in the string, right? That's the minimum, that's the least force there can be, right? So at this time, the ball just barely makes it around the surface. So I'm going to write Fc1 is equal to string force 1 plus Fw, but I'm going to put 0 in for my string force.
Should we draw it?
No, you don't need it, I don't think, right? Right? You'll now see that you've got what on both sides of the equation? Mass, and you get V min squared over r is equal to g, and so the minimum velocity is equal to square root of the radius times g. In other words, the mass of the car doesn't matter. The mass of the rubber stopper doesn't matter. The only thing that matters is what? No. To find the minimum speed, to find out how fast you have to go around, the only thing that matters is the radius and gravity. It doesn't matter how fast or how big the car is. It doesn't matter how big the guy in the car is. None of that matters. The mass cancels. Okay, so this value of V min is called the critical velocity. It depends only on the radius of the circle and the acceleration due to gravity. It does not depend upon the mass of the object in motion. Now, a satellite in orbit, like a TV satellite or what have you, some kind of communication satellite, even the space station, actually moves with the critical velocity for its radius of orbit. The moon itself, as it orbits the Earth, actually moves with the critical velocity for that particular distance away. If it moved faster, what would happen? It would get bigger and bigger and bigger, and it would take off in space. And if it was less and less and less, then it would eventually crash into the Earth, killing us all.
Just like Majora's Mask, like Zelda.
Yeah.
Maybe that's where it was.
I don't know what you're talking about, but sure.
Skull Kid made the moon slow down and crushed them.
Yeah?
Crushed our clock down.
Kids should have paid attention in physics class, right? You should note that if I were talking about satellite questions, that the radius of orbit for satellite is actually equal to the radius of the planet, such as the Earth, plus its altitude. So I just need to describe this diagram a little bit better here. So if you're talking about this distance here being RE, radius of Earth or radius of planet or whatever, and this distance here being the altitude, then the radius of orbit is actually equal to radius of the Earth or planet plus the altitude. In other words, you have to measure the radius from the center of the planet. Okay? Well, how do they determine the radius of the Earth?
Yeah, you find circumference, you get diameter.
Big string. Yeah.
Run around. You get one of those little like
Trundle wheels.
things,
Yeah.
you walk around.
The radius of the Earth is 6,400 kilometers. There's your useless fact for the day. Because I've been teaching this for a lot of
Walks
years.
around the earth with a string.
Yes. I paced it off like at the golf course. 1, 2, 3. Oh, what was that again? Go back.
What do you mean pace it off?
1, 2.
Yeah, like why do you
I walked around here and paced it off 6,400.
Yeah, why do you have to do that at a golf course?
Are you trying to figure out how far you are away from, like, you know, if you're at the 50-yard marker's there and you're like, you know, okay, so you count off to the 50, okay, I'm 64 yards to the green.
Oh. Jeez. Oh, get on that ball. I've never paced.
No?
Here.
What's here?
Yeah.
I wonder what that is. Big black square.
Just give me the bottom.
All right, last sample question. A 0.5 kilogram body moves in UCM in a vertical circular radius 1.5 meters. Period of 0.5 seconds. Find the speed of the body in its orbit, the average centripetal force needed to maintain this motion, string tension when the mass is at the bottom, and the string tension when the mass is at the top. Okay, so part A. We need to find the speed of the body in its orbit. What's a uniform circular motion formula that you know that has v in it, or speed? Well, I'm going to use 2 pi r over t. Fortunately, I gave you everything you need to know at the start.
Yay.
So 2 times pi, the radius is 1.5, and the period is 0.5 seconds. Now, I might give you that data, I might give you the period in the form of frequency. You might have to make a conversion, but I made it pretty simple here on this one. I get 18.8 meters per second. That is pretty fast, isn't it? 18 times 3, 20 times 3, it's about like 60 clicks.
Yeah, circle.
Okay, moving on.
Right.
What is the average centripetal force needed to maintain this motion? Now, is this speed, is this constant speed, or is this average, or is it instantaneous?
Average.
Yeah, this is actually average, right? It should be v bar, right? Because we're talking about the distance and the time. So it goes faster than that at the bottom, and it goes greater than that at the top. So now in B, when I'm asked for the average centripetal force, I can use that average speed using this new formula here, Fc equals mv squared over r. mv squared over r.
Do we have any of the problems like that? The Earth orbit, like with the F and the RD?
Yeah,
That's
Yeah.
what it is. You just have to have.
yeah. There are some like that, Sean. Yes, I've got a sheet that says satellite questions. So we'll get there. Yeah, we'll get there. You just got to know how to calculate that r. That's all, right?
So you just have to.
Yep, Fc, centripetal force. So the mass is 0.5. The velocity squared is this number here that I just calculated, 18.8 squared. And the radius, 1.5. So I get a centripetal force, an average of 118 newtons. You could say that the average string tension is 118 newtons. But we know that it's going to be more than that at the bottom. It's going to be less than that at the top, right?
So what is that FC right there?
That's the average,
Average.
right?
So what is the 118 newtons? That's the average?
That's the average. You could also think of it as, it would be the string tension right there, right, on its way up, or right there on its way down, right?
Okay.
So now the question is, how much do you have to add and subtract due to gravity? Now,
Those forces would be the same though, right? Just positive.
just different directions, that's right. Now here, I've always struggled in the past with this. I've had students struggle with this. If you keep in mind that the force at the bottom has to be more, and the force at the top has to be less, and don't worry about making the signs work, it'll all work out, right? I mean, we can make the signs work, you got to sort of think it through a little bit, but more or less, it's got to be more at the top and more at the bottom and less at the top, right? So the string tensor when the mass is at the bottom. Bottom equals more. Okay, so the net force is equal to 118. The net force is the centripetal force, and that 118 is made up of string force plus weight force. Where at the bottom, what direction is the net force? Up, which we're going to denote as positive. So I'm going to leave this as positive 118. Which direction is the string force? Well, that's what we're trying to find. My weight force is going to be 0.5 times minus 9.8. Or,
Okay, shut up for a second.
yeah, be quiet, you guys. Half of 9.8 is 4.9. 118. And when I take that minus 4.9 to the other side, it becomes positive, and my string force is increased. I've done it properly here with the correct signs. What's going to be different about D?
Well, you have a different formula for D.
Well,
The bottom is FC2 equals FS2 minus FS.
yeah. I'm going to show it to you with exactly the same stuff here. In fact, I'm going to be so confident about this, I'm going to copy all of this. And I'm going to go to the next page. Can I go to the next page? Okay, but this is D, right? Which way is my net force now? It's down. So the net force is actually minus 118. So the only difference is that minus in there. Is the gravity still exactly the same? Yep. Negative there, negative there, negative there. When this minus 4.9 comes to the other side, it still becomes plus 4.9. And so the only difference is now I have minus 118 plus 4.9. Minus 113.1 newtons. It's exactly the same process. The only difference being that net force at the start was negative.
So can you always do that?
Yeah, why not?